Okay, so to start off, um, let's just go to the course website really quickly. Um, okay, so on this site, you'll see some of the objectives for the class. There's the prerequisite assignment, which just do that tonight and have it ready, send it in by tomorrow morning. Below, you'll see just a note about the labs, and then you'll see some resources below. If you'd like more information on parallel programming, there are some good resources available here. The class text is this tutorial on learning MPI with Python that we've developed for the class. Um, oh yeah, it was working just a little earlier. Okay, well, I'll look into that. For now, I have it saved here. Okay, so this is the text. It's a short outline. There are just a few chapters. We're going to try to go through everything, and then the assignments for this week will just be the exercises at the end of each chapter. So we start with the preface. We talked about these in the just now. We talked about why MPI for Python. So in this overview, we talked about the limits of single processor systems. Flint's taxonomy. This is just a little information about different parallel architectures. Um, there are machines that use single input, single data, multiple input, multiple data, multiple input, single data. There's a little dispute about how to classify MPI and the systems that use MPI, and you can read over this on your own, and it shouldn't be too difficult. And then there are just a few questions to answer at the end, and we covered those in the previous video. So let's just go straight into the MPI, our introduction to MPI. Okay, so I know that we missed, or we missed the dates on the preliminary assignment. So I'm just going to demonstrate that real quick as our first parallel programming. So if you're running Windows, you pull up WinSCP. We can open our terminal. Okay. And basically, what I wanted us to do is that we would submit our first test job. We would submit it through the PBS scheduler on the Fulton supercomputer. If for just really short developmental jobs, typically you should be doing development on the interactive node, but I find that it's helpful just to run programs this way. So for the most part, we're not going to have to submit actual jobs for all of the assignments that we're doing. There are a couple that we're going to be timing our algorithms and kind of push the limits for those. We'll definitely have to submit actual jobs. But for short ones, we can simulate MPI by running them real quickly just in the command line like this. So this was the result from the preliminary assignment that you should get. We can run a parallel programming using MPI_EXCC here. We specify how many processors that we'd like to use here for, and then the application test job. And we run it, and this is the message that you should get. So you notice each process is printing to standard out, printing to the screen. We're getting a message from process 0 through 3. One thing to notice about this being the typical Hello World program, one thing to notice is how it prints. It doesn't print in order. And so that's kind of the first subtlety to notice about parallel programming. You send out 4 separate applications. They're all running independently. A lot of the time, they're going to have access to their own memory. Each processor that the actual process is running on might have different hardware specifications. There's a little randomness in there. They might be scheduled and distributed out and started at different times. And so every time you run this, you're going to get kind of a random ordering. And that's the first thing to notice about MPI, is that a lot of the timing of all of these processes, they're not going to be in sync. They're going to be far from it. And so that's one of the main difficulties of coordinating the work between all of these different processes. So that's our first application. Okay. So let's go back to the manual. Okay, so we're going to do the same thing in Python. We're going to do our first program in Python. You can type this out. I can put all these files into our shared directory. So if you want to just run them there, you can do that. But for this first one, we can just type it out ourselves. So the way that I would do that is find the directory that you're going to be working in. So for me, I'm going to do everything in. Okay. So to start off, so that first test job that we ran was compiled. It was written in C, and the second one we're going to do the same thing in Python. So let's create a new file. We'll call it hello. In the videos, I recommended the way that I like to create files and edit files. You can use VI, but the way that I prefer to do it is I'll save this file. So now I have hello.py in my directory, and then I just like to edit everything through WinSCP. So I can double click here, and I'll open it up on my own. It's actually on my hard drive now, and I'm editing it on my own computer. So let's add in the things that we need. Okay, so to start off, we're going to have to import from the MPI4py package. We're going to have to import the MPI module. And then to initialize MPI, or for convenience anyway, we are going to save what is called a communicator, and we're going to save it as com. A communicator is sort of an abstract object. It tells us about the world that we're working on. So this um, MPI com world is the default, and it just refers to all the processes, whatever they may be, however we specify them. It refers to all the processes, and it numbers them from 0 to if there's n processes, it would number them from 0 to n minus 1. And so we have different processes. Here, com.getRank is the first MPI function that we're going to learn. This is a function just to learn about that world that we're working in. And then we're going to print. So the rank is going to be the number assigned, the ID assigned to a particular process, and we're going to print that rank. Okay, so the important thing to learn about the way MPI works is that this code, it might not make sense at first, but this code is just one single code. But this code is going to be distributed to all the processes. The same exact copy is going to be sent out to everybody, and everybody is going to run the same code. All processes are going to run the same code, except MPI is going to assign a different rank to each process. And so the way that we can differentiate between processes is by that rank. So this code is sent out to all the different processes. Everybody's going to import, everybody's going to save MPI com world as com, and then everybody's going to execute this function getRank. Just to note, getRank is a method in this communicator. That's something particular to the Python implementation, and also I think it's the same in the C++ implementation. Otherwise, in C, you would just run getRank, and com would be an actual argument that would lie within here. And here it is it is an argument for within the getRank method, but Python is running MPI object oriented. Okay, so every process has a copy of the same code, but every process is assigned its own rank. So when each process runs this code and it gets to com.getRank, it goes and finds out its rank, but when it saves rank, or when it saves that number into this rank variable, each process is going to have its own rank variable, but each process is going to have a different value. So that's one thing to note. Each process that this is running on has its own variable rank, and they can all be different. And they all are going to be different, unless we specify it that way. And so then when each process then gets to this print statement, it's going to print its value of rank along with this message. And so we're going to run it using this command. So first let's type this in. Okay, one of the cool things about this is I can just hit save and it'll automatically propagate the changes to the supercomputer. So if I look at hello.py again, I can see that it all worked out nicely. Except that's a little missing. Well, let's see if it works. Okay, so let's run it. So this is different from the C version. Instead, we have to, when we call the MPI executor, we have to, the application that we're actually calling is the Python interpreter. And then as an argument, we put in the file name. Yeah. What's that? No, so you can install MPI4py on your own computer. You'll have to install an MPI implementation as well. But if you do that, then you'll just have to call Python, because on the supercomputer they have two versions of Python. They have like Python 2.3 and 2.6, and we don't want to use 2.3, so we have to specify the 2.6. Otherwise, normally it'd just be Python. Yeah. Okay, and hopefully. Okay, so we got the same thing. Hello from process, and then the process rank, and they're not in order. Okay, so does anybody have any questions about how that worked? Okay. Um, okay, so the files. I I can copy over these files real quickly, so you can try them on your own. I'll copy them over to. It uses an application called Secure Copy in Unix. That's what the SCP is. I still have to figure a few things. Okay, so it should all be there now. And if you want, you can try to run it. So okay, so uh-huh, right. Oh, okay, yes, okay, yeah. So VIM. So let's do a new file. So in VI, there's two modes, or this is VI improved. There are two modes. There's like a command mode and an input mode. So the default, you start off in the command mode, and that's where you can, usually you'll press shift and then you'll hit colon, and it'll bring this colon at the bottom, and then you can input commands that you want to run. So Q would just be to quit. Sometimes it won't let you quit. You can override that with a bang. Shift and colon, or just colon. Well, yeah, just colon. To save, if you want to save that as your actual new file, you hit W for write, and then you can also append the Q, so it'll save it and quit. Also, you might be in insert mode, which is something. If I hit I, then it brings the insert at the bottom, and then I can type some things, and I can insert anything. And then if I want to get out of insert mode, here, just hit escape, and it'll bring you back to command mode. Press I to go to insert, escape to go back. So I've typed some stuff, I'll hit escape, and then I want to save this and quit, so I'll save. I could just save, or save, and then I'll quit with W and Q. And so now I have my new file, .txt, and then I'd like my preferences just to refresh and then edit that through WinSCP. And then let me just delete that. One thing I recommend when you're deleting things is to use the I option. And it just means interactive, so it'll prompt you before you delete anything, just in case you might accidentally delete something you don't want to. So hit Tab to finish, and delete it. Yes. Okay. So any other questions? Okay. Okay, so just to note about the program that we just ran. So if you notice, so again, every process has a copy of this code, and it has its own memory, so its own set of variables. So you notice every process is calling this print. So every process is printing to standard out, every process is printing to the screen. Typically that's bad form. There are a lot of implementations of MPI and a lot of systems that won't allow you to print to the screen, to print to standard out from every process, because they exist on all these different nodes everywhere. But we're going to be using this throughout the class for pedagogical reasons, and actually for debugging, it can be a really great tool. This system and actually all the systems that I've used have allowed I/O to take place on every process. So I find it's pretty convenient to debug. If you want to see if your algorithm's running correctly, you can print out all the variables, and they're coming in from all these different processes, and you can see if it's working the way you want to. Okay, so let's go back to the manual. We talked about using I/O for debugging. We talked about how to execute the program. MPI.exe launches and it calls. It starts a whole bunch of instances of Python, and Python grabs the file that it needs. We can run it with as many processors as we want. Here we're just using 5. When we're developing, we're just going to be using just a few processes just to get our codes working. But if we want to do some serious computation, a lot of times we're going to be running with thousands of processes here. The Fulton supercomputer, I think it has a little over 10,000 cores. So you could get almost 10,000 here. A note about the COM in our code, this communicator. So again, that is probably one of the most important things about MPI, and we're going to talk about it later. But we need to learn a few other things first. But the thing that makes MPI so great are these communicators, because it allows for code to be portable. So if you ask anybody, if you ask, uh, if you ask somebody familiar with the scene, and you ask them about parallel programming, they're going to say that the biggest problem is the availability of software. Software is developing. It's still developing. There's some good software out there, but still, it's not mainstream. MPI, the standard, allows for truly portable code. So MPI will work on most any system, and these communicators are a way with dealing with an arbitrary number of processes. The MPI COM world is the default, and um, it refers to all the processes, but we can abstract our code to deal with just a few processes. Maybe we're gonna organize our processes into a grid or some kind of toroid or a circle, and we want to specify communication only on maybe a row of this grid or a column. Um, Communicators allow for that to be done easily, and it allows us to create functions and subroutines really quick, or really conveniently in MPI. So there are two types of communicators. There's intra-communicators and intercommunicators. We're not really going to be talking about intercommunicators here. Intercommunicators are dealing with explicit communication between two separate communicators. Um, this can be important later on, and it's especially important if we're running systems that allow for dynamic creation of new processes and new threads, which are becoming available more and more, but standard MPI, we're not going to be, we're not going to be dealing with that. Intercommunicators are just these blocks of processes that we were talking about. Most of the methods that we're going to be using are methods within within intercommunicators. They all mostly fall under the communicator class. Um, but really they're working with only intercommunicators. Okay, so now we're going to introduce, well, in a second, we'll introduce two functions that help us to find out about the world that we live in, the communicator that we live in. That's get size and get rank. We already talked about get rank. Get size is pretty similar. And then we're going to apply those and move on. But I guess first we'll take a break.